I think that learning assembly language will change how you see software forever. I recently read an article on medium.com called "Why Are We Still Programming in Assembler" by Jurjen Brofs. It was a good article and it got me thinking about my relationship with assembler language programming and how it impacts on my thinking, even though I haven't written any code in assembler for some years now. So that's our topic for today. Why I think it's still useful for any programmer to understand at least the principles of this most fundamental level of programming, even if they don't use assembler programming in their work. Hi, I'm Dave Farley and welcome to the Modern Software Engineering channel. If you haven't been here before, please do hit subscribe, and if you enjoy the content today, hit like as well. And why not join us in the conversation underneath the video afterwards? I started to learn how to program in the early 1980s. My first access to a computer and programming was via a Sinclair ZX81. This computer had a Z80 processor and 1K of RAM. It came with a ROM-based version of the basic programming language, which I did learn, but with a clock cycle that was around 5,000 times slower than a single core in a modern processor. So programs written in BASIC were really pretty slow and took up a lot of that rather tiny memory. So if you wanted to do anything that was really interesting, you usually had to resort to programming in assembler. So I, like most other programmers of my generation, learned assembly language programming, so we could do the more interesting things with the computers that we had access to. I started with Z80 and then later learned 6502 and then 8086 assembly language programming from Intel processors. I did quite a lot of all of these. These languages are named for the chip because that is really what assembly language programming is all about. It's the language of the hardware. It's how the processors at the heart of a computer actually do anything useful. And this is the primary reason that I think understanding at least the principles of assembly language programming is so helpful, because it's fundamentally about understanding how computers do useful work for us. There's certainly a degree to which most programmers don't need to think about this stuff most of the time. But it's a bit like chemists having a model for how atoms and so how molecules work, or how a carpenter understands the fundamentals of how the grain in the wood that they work with affects what they can do and what they can't do. These are the foundational concepts on which our discipline rests in a very fundamental sense. Let's be clear about this. Whatever it is that you are doing with any computer, you're running machine code to achieve that thing. And assembly language is really just the human readable version of machine code. So these instructions are the atoms from which all computer function is built. It doesn't matter if we are talking about making a phone call, browsing a website, playing a game, keeping somebody's heart beating with a pacemaker, or talking interactively with a large language model. Fundamentally, all of these things and everything else that a computer does are just working through a sequence of assembly level instructions. Let me pause there and say thanks to our sponsors. We're extremely fortunate to be sponsored by Equal Experts, Transfig, and Mailtrap. Equal Experts is a multinational consultancy built on applying the ideas and techniques that we talk about here on the Modern Software Engineering channel every week. All of our sponsors offer products and services that are very well aligned with the topics that we discuss on this channel every week, though. So if you're looking for excellence in continuous delivery and software engineering, do check out the links in the description below. Earlier, I said that assembly language was the language of the hardware, and that's nearly, but not exactly true. Assembly language is the human representation of the language of the hardware. Machine code is the binary instructions that our CPUs actually execute. But the key point here is that there is a one-to-one map between machine code and assembly language. There's no real difference in the level of abstraction between the two. So assembly language is really just a more human-friendly representation of machine code. So forgive me if I'm sometimes a bit lazy in saying assembly language when perhaps I should have said machine code or vice versa. I'm doing this sort of on purpose to make my point of the value of being able to at least understand the concepts that assembly language helps to make clear. Machine code is important, but less useful to us because it's harder to read. Black Friday is on its way, and there will be a site-wide sale of our whole range of world-class training courses. We have courses designed to help you master continuous delivery, understand deployment pipelines, or excel at automated testing. These courses enable you to conquer the challenges that you face, meaning that you can truly create better software faster. From the 24th to the 28th of November, there will be a 40% discount across all of our single courses and 25% off our bundles. If you want to jump the queue and get even better discounts than this, check the link in the description to our mail list. This sale is only for Black Friday week, so whether you're buying for yourself or for your team, if you want to make the most of the opportunity to learn the very best practices in modern software engineering, make sure that you follow the link in the description below or find the pinned comment. Now, back to assembly language. Fundamentally, what we are talking about here is something that my team and I started to refer to as mechanical sympathy a few years ago. That is, understanding enough about how the machines that we depend upon really work to be able to reason sensibly about them and so improve our ability to take advantage of them. There's a lot more to mechanical sympathy than only understanding assembly language, but understanding things at this level certainly plays a part. The idea was born out of my team's experience of working on ultra-low latency code when building the LMAX financial exchange. And this level of understanding was pretty much essential, and so certainly an obviously useful tool in that context of very fast computing. It became so important to us, though, that we used to ask potential team members when we interviewed them to describe how they thought a computer worked. Some of their answers were so vague and sometimes so badly wrong that sometimes they were funny. It was hard to imagine how you could write any software that worked at all with that kind of understanding of how a computer worked, let alone low latency code that maximized the use of this hardware. But clearly, not everyone needs those skills as part of their daily work. These days, not every programmer learns how to program in assembly language. Many universities don't even teach it. And I can understand the reasons why that's the case. Writing assembly language by hand is a minority sport. There are very few types of programming that demand it. Even low latency systems and embedded systems are often written in higher level languages these days. And hand optimizing the level of machine code is rarely a good investment of time, except in the most esoteric of cases, even in these already somewhat esoteric parts of our discipline. But I still think that knowledge of assembly language is more important than that, even for programmers who never write any real programs this way. It represents a literal specification of what's possible with our hardware. So understanding the basics, the principles at play here, it seems to me, a valuable tool to have in our toolkit. I think that this goes further than squeezing every last drop of performance from a system, or cramming more features into a tightly constrained hardware device. These assembly language instructions are the atoms from which everything else is built, and so they are the fundamental description of how everything else actually works. There's part of me that builds my understanding of software and software systems from these tiny building blocks. Not literally, perhaps. I don't mean that I think about the underlying assembly language instructions for everything that I do, any more than I think about how electron shells and hydrogen and oxygen atoms work when I drink water. But really, this model does underpin how I think about systems and how they work. If I'm presented with something new to me in computing that I don't understand and that seems a bit like magic at first, I will be trying to think about how this can possibly work, given my understanding of the fundamental building blocks that I know are what's really going on at the bottom. I have a mental model for how a computer works, and so understanding of how the parts of system that depend on computers must be working in reality. This helps me to think about what's going on, to reason about those systems at any level of detail. There is no level, at least down to the functioning of opcodes and registers, basic memory access and simple I/O, that I don't have to give up and say, I don't know how that works. It seems to me that this is a pretty definitive, solid kind of foundation to my understanding. Without this, at some level, I would have to shrug and say the equivalent, and then magic happens and we get a result, which, if you're a nerd like me, is never good enough. I don't mean that I'm smarter than anyone else because of this, but this is the equivalent of knowledge of basic science or maths, a foundational platform on which any reasoning about computer systems and how they work is built. If you know the fundamental of atoms, you can understand how molecules work. The enormous emergent complexity that can arise from those interactions of atoms and molecules is a different kind of problem. So I would be an idiot to claim that I understood every software system just because I understood the fundamentals of how they work. Because like molecules, the emergent behaviors from the combination of collections of individually minute steps, represented by assembly-level instructions, can be nearly as complex as the life itself. But nevertheless, at some level, this is still true. So in the same way that a chemist or a biologist can look at the workings of any chemical or biological function and only really understand what's going on after a lot of thought and study about how those fundamental parts of the system combine to deliver the observed outcomes, we can do something very similar if we have a good understanding of the fundamentals of our discipline. This probably feels a bit esoteric and philosophical, so let me try and link this a bit more concretely to things that we might care more about when developing things in the real world, even when those things are seemingly very divorced from these fundamental properties and behaviors of the machines that we're attempting to instruct with our code. One of my observations as a long-time programmer is that many programmers that I meet make some poor choices because their model of how things really work is not really very good. For example, high-level languages and operating systems layer many abstractions on top of the assembly language and what it can actually do. So, for example, an instruction to increment the value of a variable like I++ is not atomic at the level of machine code. It takes several steps, several instructions to load a register from memory, increment the value that's in that register, and then store the result back into the appropriate memory location that represents the value of the variable in your higher level language. All of this, even before we begin to think about more complex data type like floating point numbers that wouldn't necessarily fit into a single register. So if you're doing this in a concurrent system, this sequence of steps could be interrupted at any point in a whole variety of places. And that would mean my result, when my sequence of individual steps was completed, is not really very predictable. It's impossible to tell what's going to happen unless we know what else was accessing the same memory in other threads of execution. So even within a single, seemingly simple instruction in a high-level language, there's an awful lot that could be going on, and a lot that could be breaking your code in the process. This understanding makes me inherently nervous and a bit suspicious about any form of concurrent code. And that's a good thing, because if this doesn't make you nervous, you don't really understand the problem. The other common example that occurs to me is the use of multiple threads or processes in a program as a tool to speed things up. How do you speed a program up? Many programmers think that the default answer to this rather complex question is to run more stuff in parallel. But things are much more complicated than that. Sometimes this is the correct answer. Sharding the data and computation and running them on independent devices is certainly an important approach to scaling things up at very large scale. But our ability to do that and how we should approach it depends very deeply on the nature of the data and the problem that we're trying to solve. Many programmers think that adding more threads or processes will speed things up, but this is actually rarely the case. Many problems don't benefit from running in parallel. Certainly, if we can get each core in our CPU doing some useful work with little or no sharing of data between them, then this is going to be faster than running the code in a single core. But there are lots of caveats in that description. What happens if I create more threads in my program than there are cores in my CPU? What if one thread is waiting for the results of another? The answers to these questions is that things will go more slowly than making progress on a single thread, because the CPU and probably our operating system now has a lot more work to do, time slicing and switching tasks between threads and coordinating safe access to shared data. Only at the level of genuinely independent tasks running on dedicated cores do these things genuinely do the least amount of work, and so end up with a faster result. Thinking about what's happening at the level of assembly language and how processes work allows us to better understand this kind of thing. So if we ever write a program that creates more threads or processes than there are cores in your processor, then our code is probably slower than if we'd allocated work differently. This may still be an okay choice if it makes our code clearer or easier to understand. My point isn't that don't use threads or parallelization. It's just that we need to understand what's going on a bit to be able to make the best of these tools. In general, just adding more threads is a way to slow things down rather than to speed things up, because now your computer has a lot more work to do. I think that my analogy of assembly language instructions as the atoms of our discipline is a rather good one. And I feel like this is at the core of my understanding of how computers work, and so deeply influences my thinking all of the time. But to be honest, I don't feel like I've found the killer example that demonstrates to you exactly what I mean. So if you can see what I mean and have a better example, I'd love to hear it, so do let us know in the comments. And if you don't already understand how assembly language works, I'd still recommend that you learn at least the basic principles. I've included some links in the description that I think may help to get you started. So thank you for watching to the end, and I'd also like to say thank you to our Patreon members who support this channel and allow us to do what it is that we do here. Thank you as ever for your support. And if you're interested in joining as a Patreon member, there's links to that in the description below too. Thanks and bye-bye.